Hello everyone, welcome to this video lecture of this course Finite Element Method. So this is the continuation of this last lecture where we have discussed some numericals based on the Rayleigh Ritz method. Okay, so there we have seen that in case of this Rayleigh Ritz method there are actually 7 different steps and we need to follow those 7 different steps to solve the different numericals based on the beam or bar element, and there we have to identify the bending moment or maximum bending moment in case of the beam or bar element. So those 7 different steps are very much important, based on which we will solve different numericals on this Rayleigh Ritz method. So today also we will continue that lecture. That means today also we will discuss some more numericals based on those Rayleigh Ritz method, and after that we will discuss regarding the initial and boundary value problems. Okay, so let us start this lecture. So the numerical that is given here, a beam AB of span L simply supported at ends and carrying a concentrated load W at the center C as shown in figure. Determine the deflection at midspan by using Rayleigh Ritz method and compare with exact solution. So the diagram it is given here, one simply supported beam, and the length or the span it is L for the simply supported beam, and it is carrying a concentrated load W at its center. Now we need to find the deflection at midspan, that is the maximum deflection at point C we need to find here. Now as this is a beam element, so that's why in the first step, while considering the approximation function, we will consider the trigonometric function. In case of bar element, we have to consider the polynomial function. So as this is a beam element, so we will consider the trigonometric function which we have got from the Fourier series formula. Now in this trigonometric function, that is the approximation function, there we have considered only the first two terms of the Fourier series, having the two different Rayleigh Ritz parameter which are a1 and a2. So the approximation function here, this is the first step, it is y equals to a1 sine pi x by L plus a2 sine 3 pi x by L. So this is the first step where we have selected or identified the approximation function from the Fourier series in case of this beam element. So in the next step, we actually need to find the value of the strain energy. So this is actually capital U. Now the formula for the strain energy, this is U, this is equals to EL by 2 integration 0 to L d2y dx2 whole square dx. So this is the formula for to calculate the strain energy. Now in this numerical we have calculated or we have identified the approximation function y in the earlier page. So we need to find the dy dx and d2y dx from this equation. After finding this value of d2y dx, to that formula or that value of d2y dx2 we need to put here in the formula of strain energy. After that, one lengthy process is there to find this value of u that we have seen in the last lecture. So there we have done some integration and some formula for trigonometry we have used, and after several steps we have ultimately calculated the mathematical representation of the strain energy U, that is actually EI p pi to the power 4 by 4L cube into A1 square plus 81 A2 square. So it was the mathematical representation of the strain energy. So in this numerical we have skipped all those steps and we have directly written the mathematical representation of the strain energy. So it is the second step of the Rayleigh Ritz method. Next, in the third step, we have to calculate the work done by external force. Now, the work done by external force in case of this beam element, it is equal to Wy max, and this Y max, it will be the deflection at maximum point, that is the deflection will be maximum at x equals to L by 2. So the Y max, it can be calculated by putting the value of x equals to L by 2 in the formula of y, or in the mathematical representation of y. So after putting that y equals to L by 2, we have calculated the Y max. This is equals to A1 minus A2. Now if we want to find the value of the total work done, capital H, that means W into Y max, so it is W into A1 minus A2. So this is the end of the third step in case of this Rayleigh Ritz method. The next or fourth step, it is to calculate the total potential energy, that is pi equals to U minus H. Now to calculate the total potential energy of the beam, pi equals to U minus H, that means we need to put the value of U and H in this formula of the pi, of the total potential energy. So that means we are getting the mathematical representation of pi as EI pi to the power 4 by 4L cube A1 square plus A2 square minus W into A1 minus A2. So this is the equation number 8, and it is the end of the step 4. That means we have calculated the total potential energy. Next, in the fifth step, we need to find the value or the mathematical representation of the Rayleigh Ritz parameter A1 and A2. So for that, what we need to do, we need to do this part, that is del pi del A2, this is equals to 0, and del pi del A1, this is equals to 0. These two things we need to do. That means to find the value of the Rayleigh Ritz parameter A1 and A2, we need to do the differentiation of the total potential energy with respect to A1 and A2 separately, and those values will be equals to 0. Now if we do this part, then after several steps we will get the value of A1. This is actually 2L cube divided by EI pi to the power 4. So this is the value of A1 that we are getting. Next, if we do this part, that is del pi del A2, so that means again after 2 or 3 steps we will get the value of A2. This is equals to minus 2L cube W by 81 EI pi to the power 4. So these are the value of the Rayleigh Ritz parameter that we have obtained by differentiating the total potential energy with respect to A1 and A2 and then equating those equals to 0. Now we need to find the maximum deflection. So the maximum deflection formula Y max when x equals to L by 2, this is Y max equals to A1 minus A2. Now here we need to enter the value of this A1 and A2, that is the Rayleigh Ritz parameter that we have found just now in step 5, and then after 3 steps we are getting the value of Y max. This is WL cube by 48 EI. Now in case of the simply supported beam subjected to a point load, the maximum deflection from the exact solution that is known to us, that is WL cube by 48 EI. Now here in this numerical, by this Rayleigh Ritz analytical method, we have got the same value. It is the exact solution and the solution obtained by using the Rayleigh Ritz method. These are same for the maximum deflection. In case of this Rayleigh Ritz method, it was 48.1, but in case of this exact solution, it was only 48. So these are almost same. Now to get some more accurate value, we need to take into consideration some higher order terms in case of the Fourier series while considering the approximation function. So this is the procedure to solve such numerical based on the Rayleigh Ritz method. So what we have done here for the simply supported beam, there are actually 7 different steps for the Rayleigh Ritz method. So the first step was to identify or to select the suitable approximation function. Now here, as it is given the beam element, so the approximation function, it will be based on the Fourier series. Now here we have considered only the first two terms of the Fourier series, uh, which are having the two different Rayleigh Ritz parameter. If it would have been a bar element, then we had selected the polynomial function at this as the approximation function. Now this is the first step to identify the or to select the suitable approximation function based on the beam element. Next, in the second step, we have to find the value of the strain energy, that is U, and the formula of the strain energy is actually given EI by 2 integration 0 to L d2y dx2 whole square. Next, in the third step, we need to calculate the value of the work done by the external force. The formula for the work done by external force equals to W into Y max. So here Y max will be when x equals to L by 2. So putting this value, we have to calculate this work done by the external force. Next, in the fourth step, we need to calculate the total potential energy. So that potential energy pi equals to capital U minus H. Okay. So in this way, we have found the mathematical representation of the total potential energy at step 4. Next, in the step 5, we need to find the value of the Rayleigh Ritz parameter A1 and A2. So for that, we need to do this del pi del A1, this is equals to 0, and del pi del A2, this is equals to 0. Now from this step, in the step 5, we have found the value of the A1 and A2, that means the two different Rayleigh Ritz parameter. And lastly, in the step 6, we have calculated the maximum deflection, which is almost same with the exact solution. Now let us discuss one more numerical of this Rayleigh Ritz method for the beam element. So it is given a simply supported beam subjected to uniformly distributed load over entire span, and it is subjected to a point load at the center of the span. Now we need to calculate the bending moment and deflection at mid-span by using the Rayleigh Ritz method, and we need to compare it with the exact solution. So earlier, what we have discussed regarding the two different Rayleigh Ritz method, in those numericals, one of the numerical was having only the uniformly distributed load, and the other numerical was related to the only point load. But in this numerical, both the uniformly distributed load and the point loads are acting on this simply supported beam. Now, how to find the deflection and the bending moment at the mid-span in this numerical. So as this is a beam element, so in our step 1, we need to find, or we need to identify the approximate solution. Now as this is a beam element, so the approximate solution, it is a trigonometrical function. So it is the first two terms of the Fourier series that we have considered here. So that means the approximation function, the deflection y, this is equals to a1 sine pi x by L plus a2 sine 3 pi x by L. So this is the first step here. Next, in the step number 2, we need to find the value of the strain energy, that means U. And in step number 3, we need to find the value of the total work done for this external force. And in the step 4, actually, we need to find the total potential energy, which is capital U minus H, the strain energy minus the work done due to external force. Now in the step 2, we need to calculate the strain energy U. Now in the strain energy U's formula, it is EI by 2 integration 0 to L d2y dx2 whole square dx. So that means for the given deflection y, from this given deflection y is mathematical representation, we need to find dy dx and d2y dx2, and that value of d2y dx2 we need to enter here in equation number 3. Now this value of d2y dx2 we have already calculated while discussing the first numerical of this Rayleigh Ritz method in the earlier lecture, and there we have seen it is a lengthy process, but it is not very complicated. We need to only use the concept of the calculus and the trigonometry. So after performing that integration, we have actually got the mathematical representation of the strain energy U. This is equals to EI pi to the power 4 by 4L cube into A1 square plus 81 A2 square. So this is our equation number 4, and it is the end of the step 2. Next, in case of step 3, we need to find the value of the work done by the external force, that means capital H. So the formula for the capital H we need to calculate in this way, that is integration 0 to L omega y dx plus W into y max. So this is actually that integration 0 to L omega y dx. This is actually applicable for the uniformly distributed load, and the second part, that is W into y max, it is due to the point load which is acting. So the work done by the external force H, this is equals to integration 0 to L omega y dx plus W into y max. Now to calculate this integration 0 to L W into omega into y dx, for that we need to use the approximation functions value here, and after several steps we will get this first part of this work done, that is 2 omega L by pi into A1 plus A2 by 3. Now to calculate the second part of this work done, that is W into yx, for that we need to find the value of y max, that is the deflection is maximum at x equals to L by 2. So when x equals to L by 2, for that we need to find the y max, which we are getting as y max equals to A1 minus A2. Now this value of y max we need to put there. Now after putting that two different work done due to the different loads, that is uniformly distributed load and point load, in the total work done formula, that is H, we will get this equation number 8, that is 2 omega L by pi to A1 plus A2 by 3 plus W into A1 minus A2. So this is the mathematical representation of the work done due to the two external forces, that is one is for the first part is for the uniformly distributed load, and the second part is for the point load which is acting on the beam at its mid span. Now to get the total potential energy, we need to write the equations of U and H here. Now if we write the equations for U and H, then we are getting the equation number 9. This is the equation for the total potential energy here. Now for the next step, we need to find the value of the Rayleigh Ritz parameter. So to find the Rayleigh Ritz parameter, we need to do these steps, that is we need to do the differentiation of this total potential energy with respect to A1 and A2, and we need to put those equations equals to 0. So that means del pi del A1 this will be equals to 0, and del pi del A2 this will be equals to 0. Now for the first part, if you do this part, that is del pi del A1 equals to 0, so that means we are getting that EI pi to the power 4 L cube into 2A1 minus 2 omega L by pi minus W, this is equals to 0. So that means after two more steps, we will be getting the value of A1. This is equals to 2L cube by EI pi to the power 4, then bracket 2 omega L by pi plus W. So this is the value of the Rayleigh Ritz parameter A1, that is equation number 10. Next, to find the value of the Rayleigh Ritz parameter A2, we need to do this part, that is del pi del A2, this is equals to 0. So that means we are getting this part, that is EI pi to the power 4 4L cube into 162 A2 minus 2 omega L by pi into 1/3 plus W. So from this step, after 3 more steps, we will be getting the value of the Rayleigh Ritz parameter A2. This is actually coming as 2L cube by 81 EI x to the power 4 into 2 omega L by 3 pi minus W. So these are the values of the Rayleigh Ritz parameter A1 and A2. Now, to find the maximum deflection, the value of the maximum deflection, it is already known to us, that is y max equals to A1 minus A2. So this value of the A1 and A2 we have already calculated in the earlier step. Now we need to put this value of the A1 and A2 here. Now after putting this value of A1 and A2, we will get the value of y max, that is as equation number 12, where we can see the representation of y max. This is 0.0130 omega L to the power 4 by EI plus 0.0207 omega W L cube by EI. Now we need to compare this deflection with the exact solution. So the exact formula, that is this simply supported beam subjected to a uniformly distributed load. In that case, the maximum deflection value, it is actually 5 by 384 omega L to the power 4 by EI. Again, when the simply supported beam is subjected to a point load at the center, in that case the formula for maximum deflection y max, this is equals to W L cube by 48 EI. Now to get the exact solution of the total deflection, we need to add these two, because in this current case the beam is subjected to both the uniformly distributed load and point load. So that means the value that we are getting here, that is for the exact solution, the value, it is we are getting 0.0130 WL to the power 4 by EI plus 0.0208 WL cube by EI. So that means this exact solution and the solution obtained by the Rayleigh Ritz method for the maximum deflection, in this case, these are almost same. Okay. Now for the last part, we need to calculate the bending moment at the mid span. Now to calculate the bending moment at the mid span, the formula that we will use, it is m equals to EI d2y dx2. Now here we need to put the value of d2y dx2, that is from the approximate solution of y that we have considered in the first step, that is y, it is the first two terms of the Fourier series. So from that step we need to find the d2y dx2, which we are getting here as minus a1 pi square by L square sin pi x by L plus a2 9 pi square by L square into sin 3 pi x by L. We need to put this value in the formula of the bending moment, which is m equals to EI d2y dx2. So at the mid span, x equals to L by 2. So that means instead of this x, we need to put the value of L by 2 here. Then after several steps and using this value like sin pi by 2 equals to 1, sin 3 pi by 2 equals to minus 1, using all these values, and after 8 or 10 different steps, we will be getting the value of d2y dx2. This is equals to minus 0.124 omega L square by EI plus 0.225 WL by EI. So that means the maximum bending moment at x equals to L by 2, we are getting that minus 0.124 omega L square plus 0.225 WL. So here the negative sign, it actually indicates the downward deflection. So this is the value that we have got using the Rayleigh Ritz method. Now we need to compare this with the exact solution. Now when the simply supported beam is subjected to a uniformly distributed load or UDL, in that case the exact formula of the bending moment, it is actually omega L square by 8. And when the simply supported beam is subjected to a point load at the center, in that case the maximum bending moment, it is WL by 4. Now that means the total bending moment, it will be the summation of these two, because the current simply supported beam, it is subjected to both the uniformly distributed load and the point load. So that means the value, exact value of this maximum bending moment we are getting here 0.125 omega L square plus 0.25 WL. So this is the exact value of the maximum bending moment, which is equation number 16. And the equation number 15 in the earlier slide, it is the result of the maximum bending moment using the Rayleigh Ritz method. So that means we can see here that the exact solution of the maximum bending moment and the solution obtained by the Rayleigh Ritz method, these are almost same. Now in order to get more accurate result, we need to consider some higher order terms from the Fourier series in the approximate solution in the first step. So this is the procedure to solve these numericals based on the Rayleigh Ritz method. So actually there are 7 different steps that we need to remember, and we need to implement such numericals based on the beam, a simply supported beam which is subjected to a uniformly distributed load or a point load, or it may be subjected to both the uniformly distributed load or point load. So for all different cases, we need to first identify the approximate solution. In case of the beam, it will be a trigonometrical function from the Fourier series. And for maximum of the numerical, we have considered only the first two terms of the Fourier series. After that, we need to calculate the strain energy in the step 2. The formula is there. Next, in the step 3, we need to calculate the total work done due to the application of the external forces. Next, in the step 4, we need to calculate the total potential energy, which is pi equals to U minus H, that is strain energy minus total work done due to the application of the forces. Next, in the step 5, we need to calculate the different Rayleigh Ritz parameter in the approximate solution, that is A1 and A2. So for that, we need to do this del pi del A1, this is equals to 0, and del pi del A2, this is equals to 0. Next, in the step 6, we need to find the maximum deflection at the mid span. For that, we need to put x equals to L by 2. And last, in the step 7, we need to find the maximum bending moment. So for that, the formula, it is also there. So these are the 7 different steps that we need to perform while solving such numericals based on the Rayleigh Ritz method. Now let us discuss some initial value and boundary value problems. Now, what are these actually? Differential equation along with subsidiary conditions on the unknown function and its derivatives, all given at the same value of the independent variable, constitutes an initial value problem. Now, the subsidiary conditions are initial conditions. If the subsidiary conditions are given at more than one value of the independent variable, the problem is a boundary value problem, and the conditions are boundary conditions. Okay, so these initial value and boundary value problems we will discuss in the next lecture and in the next slide actually. So the concept of this initial value and the boundary value, these are very much important when we will discuss the software simulation part. Initial and boundary conditions, that will be very much required at that time. Now some example are given. Suppose the problem y double dash plus 2y dash, this is equals to e to the power x. Now here it is given y pi equals to 1 and y dash pi equals to 2. Now this is an initial value problem because both the subsidiary conditions are given at x equals to pi. So how is that? That means here y pi equals to 1. This means actually at x equals to pi, y equals to 1. And for the second part, that is that y dash pi equals to 2. This means that at x equals to pi, y dash this is equals to 2. So now it is an initial value problem because both the subsidiary conditions, these are given at x equals to pi. The second example is that y double dash plus 2y dash this is equals to e to the power x. So here two conditions are given, that at y0 equals to 1 and y1 equals to 1. So here y0 equals to 1 means at x equals to 0 y equals to 1, and y1 equals to 1, this means that at x equals to 1 y equals to 1. Now this is a boundary value problem because the two subsidiary conditions given, these are the at the different values at x equals to 0 and x equals to 1. Now one problem regarding this initial value problem, it is given here. We need to find the solution of the initial value problem. Y dash plus y this is equals to 0 and y3 this is equals to 2. These are given here. So the differential equation, this is y dash plus y equals to 0, and the boundary condition is y3 equals to 2. That means at x equals to 3 y equals to 2. First we need to use the auxiliary equation. So this concept of the auxiliary equation, it is known to us. So the auxiliary equation of this differential equation, it is lambda plus 1 equals to 0. So lambda equals to minus 1. So here y dash this is actually lambda. Here the complementary function or the characteristic function, this is equals to yx, this is equals to c1 e to the power minus x. Now here if we enter this condition, but that is the boundary condition, that is at x equals to 3 y equals to 2, then we are getting the value of c1 equals to 2 e to e cube. So that means the final solution we are getting as yx this is equals to 2 e cube e to the power minus x. So this is the solution of the initial value problem. Now let us discuss one boundary value problem. So question is given, find a solution of a boundary value problem y double dash plus y this is 0 with y0 equals to 0 and y pi by 6 equals to 4. So in this similar manner we need to first write the auxiliary equation here. So that means lambda square plus 1 this is equals to 0. So that means lambda equals to root under minus 1, that means plus minus I. So that means lambda equals to alpha plus minus I beta. So here alpha equals to 0 and beta equals to 1. Now here the complementary functions, this will be yx this is equals to e to the power alpha x c1 cos beta x plus c2 sin beta x. Now if we put that at x equals to 0 y equals to 0, so that will be entered here. But first if we put the value of alpha equals to 0 and beta equals to 1, then we are getting yx this is equals to c1 cos x plus c2 sin x. If we put the boundary conditions, that y0 equals to 0, then we are getting the value of c1 this is 0, and putting the value of y pi by 6 equals to 4, we are getting the value of c2 equals to 8. If we put this value of c1 and c2 in the equation of y, then we are getting the value of yx this is equals to 8 sin x. So this is the final result of this numerical of the boundary value problem, that means yx equals to 8 sin x. So these are the procedure that we have discussed today. We have discussed two different numericals based on the Rayleigh Ritz method. We have seen how to effectively use the 7 different steps of the Rayleigh Ritz method and how to compare the exact and the solutions obtained by the Rayleigh Ritz method, and how to get some more accurate result regarding the Fourier series. Next we have discussed some concept of the initial value and boundary value problem, and after that based on those concepts we have discussed two different numericals each for initial value and boundary value problems. Okay, so this is the end for this lecture.